learn what we've... Alright, so now I want to learn... Alright, now I want to use what we've learned to solve this problem. I want to find a basis B in which the matrix corresponding to this linear transformation is diagonal. Alright, so you hear diagonal, you think I'm going to diagonalize a matrix, but I don't quite have a matrix yet. So what I would first do here, I would choose any basis I like, find a matrix for this linear transformation in that matrix, then diagonalize that and transform the basis that diagonalizes that matrix in R3, bring it back to P2. Alright, so let's try this. Let's start by finding T in some basis. You get to choose whichever one you like. Since this is P2, I'm going to use the standard basis. And I'm going to choose the order 1x squared, just because I think it's going to make the matrix a bit simpler. Alright, so I need to find what T does to all of this. If my polynomial is just 1, that will not change anything. So this is this is 1 times 1 plus 0 times x plus 0 times x squared. So that's going to be my first column. My first column will be 1, 0, 0. If my polynomial is just x, this is going to send it to 2x plus 3, which is 3 times 1, 2 times x and 0 times x squared. So the blue entries will be my second column, and T of x squared, that will be 2x plus 3 squared. I'll get 4x squared plus 12x plus 9. And so that's, let me do it in a third color. Which one works well? Maybe orange. Let's try orange. That's going to be 9, well, that's good, 12 and 3. So, what is the 3 from? 12 and 4. So that's 9 times 1 plus 12 times x plus 4 times x squared. So the matrix for T in BS would be 9, 12, 4. The middle column is 3, 2, 0. And 1, 0, 0. Alright, so now I have a matrix. I can work with this matrix. I'm going to find its eigenvalue. I'm going to find eigenbases for all the eigenvalues. Hopefully I get enough eigenvectors that are independent to build a basis so I can diagonalize this matrix. So step 2. Find eigenvalues, eigenvectors. Alright, so the characteristic polynomial of TBS will not be too bad because I have an upper triangular matrix and determinants of those are easy. You just take the diagonal. And so we end up with 1 minus x, 2 minus x, 4 minus x. And so my eigenvalues would be 1, 2, and 4. For each of them, you need to find an eigenvector. I've done it for us, so we don't need to do it again. So let's say we've done some work for lambda equals 1. I got the factor 1, 0, 0. For lambda equals 2, I got 3, 1, 0. And for lambda equals 4, I got 9, 6, 1. Alright, so that means that if I look at this matrix and this basis, I'm going to get a diagonal matrix. That's great. How do I get So this is a basis for R3. I would have 1, 0, 0. I'll have 3, 1, 0. And I'll have 9, 6, 1. So that's the basis for R3. I want one for P2. We're going to do the usual thing. We fixed a basis to start with. We fixed a standard basis. That gives us an identification between R3 and P2. That identification takes this basis to the basis we're looking for. So step 3. I want to move from R3 back to P2, so 1, 0, 0, I apply phi of Bs, so that's going to be 1 times your first basis element plus 0 times the second plus 0 times x squared. So that's just 1. Now the second one is 3, 1, 0. So that will be 3 times 1 plus 1 times x plus 0 times x squared. So it's x plus 3. And the last element of my basis for P2 would be the image of the last vector. Sorry. So I get x squared plus 6x plus 9. So my basis for P2 would be 1, x plus 3, and x squared plus 6x plus 9. Alright, so I claim that in this basis the matrix of T is diagonal. In fact, I claim that the matrix for T in this basis will be just the eigenvalues on the diagonal. So we had 1, we had 2, and we have 4. Let's double check. Alright, so to figure this out, I need to apply t to all 3 of the basis elements and then write them as a linear combination. T of 1 is 1, and that is 1 times 0, and the other one's, 1 times 1, and the other one's a 0. And so that's the first column there, that's perfect. Alright, if I take t of x plus 3, that was x is replaced by 2x plus 3, that's 2x plus 6. Oh, sorry. Made a mistake here. I meant to write this. I need to write the image in this new basis as well. Right, so to write the matrix in this basis, I take the elements of this basis, apply t, and rewrite them using this basis. So this is what I needed. Now this one, I can write as 0 times 1 plus 2 times x plus 3 plus 0 times x squared plus 6x plus 9. That would be the second column, 0, 2, 0. And the last one, so if I apply t to this polynomial, I'll get 2x plus 3 squared plus 6 times 2x plus 3 plus 9. That's 4x squared plus 12x plus 9 plus 12x plus 18 plus 9. That's 4x squared, 12 plus 12 plus 24x plus 36. And that is just 4 times the last of my basis vectors. And so I don't need the other ones. That's exactly what I want, 0, 0, 4. Alright, so far we used diagonalization to take high powers, and we've used it to find nice bases for linear transformation. In the next week, what we'll do is we'll use diagonalization to solve differential equations. We'll use it to solve more real-life problems about probability. Thank you.